Hello, everyone. Today we are starting chapter 3, which is all about transformations. So, here we've got a bunch of objectives that we're going to do over the chapter. And specifically today, we're looking at 3A and B, which is translations and dilations. So, today that's what we're learning about translating and dilating functions. What you need to be able to do is understand the notation of mapping, map a translated point, map a translation onto an existing function, and then find the transformations given a transformed function. So as we start our journey of transformations, we need to recognize the big three. So we're looking at translations, which is all about moving functions or points left and right. Dilations, which is multiplying points to make them larger or smaller, and then reflecting. And that's where you have a mirrored line, and then you can see you've got like a mirrored image. It's reflected onto the other side of it. So that's the three transformations. And today we're specifically going to be focusing on translations and dilations. So starting off with translations and really just getting our heads around, in general, the language that we use with transformations. The first things that we need to note is the notation that we use. So we're very used to X and Y. And in this case, when we look at X and Y, that is always going to tell us about our original or our old points. So it's going to be our original function that we're starting off with. And now because we are going to be changing that function, we need translated or new points. So we call that X dash and Y dash. So when translating, what we would write is that x dash y dash, as in the new x and y, new y, can be defined as, so the arrow means can be defined as, x plus h, y plus k. So that means what we're doing is that we are doing the old x plus whatever h it is, and the old y plus k. And so new x is equal to old x plus h, and new y is equal to old y plus k. And that's the kind of notation that we are going to get used to while we are writing out our transformations. Now, specifically when we're looking at translations, we can think of it like this. So we've got a 0.25, for example. When it's translated 2 units in the positive x direction, it becomes 4,5. Now, how has that happened? So this is the old x. What we're doing is we're adding 2 because it's 2 units in the positive direction. 2 plus 2 is equal to 4. And you can see that this point has moved across to become 4 over here, whereas it's 2 there. Scale is probably not the best, but that's the idea there. Now, the y value has not changed. There's been no transformation that has applied to it. So let's look at this first example, and you'll notice that with a lot of these examples, we're actually going to do it through two methods. The first one is using the dash method, which is the coordinate mapping. And that's the notation that I have just spoken about. It does take a while to get your head around it. Personally, I use it a lot for questions that are a little bit more complicated because the idea is that as long as you follow the steps, you can't make a mistake. The second method is kind of just looking at the function and figuring out what it is. For easy ones, that's totally fine. But when it gets a little bit more complicated, there's a lot more room for error. So look at both of them and you decide whichever one you prefer. I would always suggest that you learn how to do coordinate mapping because when the function gets really difficult, it's hard to just look at it and know, but it's totally up to you. Okay, so let's go through this one. Example 1 says find the equation of the image of the curve y equals f of x, where f of x is 1 on x, under a translation of 2 units in the positive x direction and 3 units in the negative direction of the y-axis. Now I'm going to give you a series of steps that's going to help you out in being able to do this. I can see that I've got two transformations here. They're both translations. So what we're going to do is we're going to apply it to our original notation. Now remember our notation said new x and new y can be defined as. So we are going to create our coordinates like before we had x plus h and y plus k. So in this case, we'll have x plus something, y plus something. In this case, we can see that it's a translation of 2 in the positive direction. So that's going to be x plus 2. And then we've got 3 in the negative direction. So that will be y minus 3. So that is our first step, which I will usually call apply. So we will apply the transformations. Now, our second step is to equate the new and the old. So again, following the notation that we just spoke about, this tells us, so step 1 tells us that new x is equal to x plus 2 and new y is equal to y minus 3. Now, how does that relate to what we already have, which is our function here? So our function, I might just write it in the bottom. y equals 1 on x. Now you'll notice that this one is old, right? There's no dashes, so that's old y and that's old x. My aim is to substitute in these here into my function. But the problem is that I've got old x and old y, so I can't substitute in new y into here because it's not the same variable. But this is the same variable as this, and this is the same variable as this. So our third step of this method is to go ahead and rearrange. So what we want to do is get old x and old y by itself in order to be able to substitute it into the function. So I'm going to do x equals 2, and so we'll just take the 2 to the other side. So that'll be x dash minus 2, and y is equal to y dash plus 3. So then our fourth step, now that we've got old x and old y, is to substitute in our variables. Substitute. There we go. Okay, so we've got the function y equals 1 on x. So this is my old. I'm just going to write that out for you. You don't need to normally write it out. So now wherever I see y, I'm going to substitute the old y in. So that'll be y dash plus 3, and then 1 on x dash minus 2. All right, now our very last step, we're almost there. I'm just going to actually rearrange everything just to give myself a bit more space to work. So that'll be 4. All right, now our fifth step is actually going to be a repeat of the previous one. And it's really about convention because when we present a function, we always present it in terms of y equals. So rearrange to get y by itself. So all I'm aiming to do now is to get this new y on its own. So new y is equal to 1 on x dash minus 2 minus 3. And so that is my new function. Now, there's something that's hopefully interesting that you can note. For the first time, you'll be able to see why whenever we are moving in the positive direction, like we're moving literally to the right, which makes us think we're adding, why is it a negative? So you've been learning all of these years that you always do whatever the opposite sign is. You can now see the reason why it is the opposite sign, and it's because we rearrange it in this step here. So x minus 2 actually means we're moving to the right. However, with the y, it stays as it is because on this side, yes, it's the opposite sign, but when we bring it back, we are rearranging it again, so it goes back to its original. So hopefully that's a nice little click for you as to why the signs are the opposite for the x, but they are the same for the y. Now, of course, we can do this exact same method, but just by looking at the graph. And this is a straightforward one. So this is one that I would say you can probably just have a look at it and know. So again, we've got 2 units in the positive direction and 3 units in the negative direction of the y. So what we want is we want x, we want to shift that over by 2 that way, and we want to shift the y down by 3. So if this is my original graph, so in order to shift x over to the right, remember it's always the opposite sign. So that'll be x minus 2. And then we want to shift the whole graph down by 3. And you can include the dashes just to be able to make, to let the people know that this is the new graph. But even if you didn't include it, it's okay. Like we understand that that's the transformed function. So obviously in this case, it is way easier to just have a look at it. But as I said, as things get a little bit more complicated, the dash method is going to be a lot more certain for you that you're doing the right thing. Okay, so that's transformations. So that's our little summary. So applying the transformation, we use this idea, this method here, and you need to remember those 4 steps. So that was to apply, equate, rearrange, substitute, and rearrange again. And the more that you do it, the more that you're going to get used to it. All right, so let's move on to dilations. And what you're going to notice is that every single transformation now, even though it's different, is going to use the exact same process. So we still have this language here. What we're doing is we're multiplying by A or multiplying by B if we're dilating. The language of dilations is a little bit more confusing, so we'll go through it specifically. But again, you can see what we would do is apply and equate. That's always our first 2 steps. Now let's talk about our first dilation, which you'll notice is called parallel to the y-axis or from the x-axis. So it could be either one. Usually we use from the x-axis, but a book could totally, or the exam could say parallel to the y. It's the same thing. Now, a dilation of a factor 2 from the x-axis. Think of we're starting at the x-axis and we're moving away from it. So that's what the word from is, moving away from it. How do we do that? So if I have my original x point, and y point, so it's not even about x, so away from the x-axis, you can see that's a vertical dilation. So actually, I'm affecting my y value. So the way to think about it is when it's the word from, it affects the opposite variable. When it's parallel, though, it's the same. So you can see that this line is parallel to the y, which is why we're affecting the y value. So dilation of 2 means we multiply every y value by 2. You can see that our ellipse or our circle has gotten larger to become an ellipse. And then when it's a half, it becomes smaller. So again, our circle has been squashed to become an ellipse. This is our mapping language, but we're going to have a look at that in a second anyway. So let's try example 2, and we're going to consider a curve with the image of y equals root x dilated by factor 3 from the x-axis. So again, we've got our two methods. I'm try and split it up. I might need a bit more space, but we'll see how we go. So first one we're going to do is through the dash, and then the second one is we're just going to have a look at it. Now, again, we're going to go through all of the steps that we just went through. So our first step was to apply. So we are defining our new x and new y as, and it's a dilation by factor 3 from the x-axis, which means every y value is getting multiplied by 3. 3y. Okay, our second step is to equate. So that means that my new x is equal to the old x, which is very lovely, and our new y is equal to 3y. Now I want to substitute it into the original equation, but as I can see, I've got old y and old x here, and that's not what I have, so I can't sub it in. I have to rearrange in order to be able to get that. So my third step is to rearrange. So we don't really have to do much for x because that's just as it is. But the y, I want to get old y by itself, so I can substitute that directly in. All right, fourth step is to substitute in. So the old x goes into the old x, the old y goes into the old y. So x doesn't really change, but the old y is like this, and that'll just be root x. And then my fifth step is to rearrange again. Again, out of this time, it's out of convention, just the fact that we usually get y by itself. So we just want to get y on its own, and we multiply by 3 there. Okay, so that is how we would complete this problem here. Now, in terms of just being able to look at it and knowing, the idea is that if it's a factor of 3 from the x-axis, that means every y value is getting multiplied by 3. Now, if y, sorry, my pen's going a bit nuts. So we're multiplying every y value by 3. Now, if y is equal to root x, then 3y would just be equal to 3 root x. So if y is equal to root x, if I want to multiply the y by 3, then I would multiply that by 3 as well. So you just kind of need to know where the transformation sits. Obviously, so much easier for this specific example. But if you're unsure, the dash method is always going to be there to help you out step by step to make sure that you get it correct. Okay, so that's just a little summary when we're talking about from the y-axis. Sorry, from the x-axis. Now we're about to start talking about from the y-axis. So from the y-axis means that we are going to be affecting our x values. So we're starting at the y and we're moving away from it. So you can see that that's parallel to x and we are multiplying horizontally. So if we want a factor of 2, we multiply all of our x values by 2. If we have a factor of a half, we're multiplying all of them by a half and we're squishing it there. So let's go ahead and complete an example for this one. So we will have determine the rule of the image where the graph y equals root x is dilated by a factor of 3 from the y-axis. So you can see that this time it's a little bit different. So from the y-axis this time, which means we are affecting our x values. So we're going to do it, I mean, in this point, you can do it sort of either way. I'm going to do it through the dash method so that you can kind of see what happens, because this one's always the tricky one that kind of gets everyone. All right, step 1, we're going to go ahead and apply. So new x, new y is equal to, so now remember when it's from the y-axis, it means every x value is multiplied by 3 this time. 2, we will equate. Old x is equal to 3x, old y is equal to, sorry, new x is equal to 3x, new y is equal to just old y, not much going on there. 3 is to rearrange. So we're just going to get the old by itself so that I can go ahead and substitute in. Again, don't have to do much for y. Fourth is to go ahead and substitute that into the original equation. So old goes into old into old there. Okay, so y is just going to be y dash. Now instead of x, though, we're going to write x dash on 3. Now our fifth step is to rearrange to get y by itself. It's already in that form. So we actually can just leave it as that. That's already done. You can write it out again, whatever you want to do. Now, hopefully, again, this is now a big click moment. Why is it that we do the opposite? So with x, again, when it's attached to x, it's the reciprocal. So we always say that if it's got if it's divided by 3, then it means it's multiplied, or if it's multiplied by 3, it means it's divided. So hopefully that's clicks to you as to why that is the case, and again, why the dash method is quite good. Like you can't go wrong with that. All right, I was just trying to draw a simple line, and my pen just decided it didn't want to. Okay, if you were to do it just by looking at it, I mean, there's not really too much to it. It's really just being able to see, okay, 3 from the x, which means it's going to affect x. That just simply means that we are going to do x on 3. So that just means from the x-axis. So you kind of just need to know that um, that's how it works. So that would just be by looking at it, you would divide by 3. Okay, just a quick summary for that one. So for the graph of this, the following two processes yield the same results. So this is kind of just everything that we just spoke about. But just remember that with x, it's always the reciprocal if you want to just kind of have a look at it and be able to try it out. So now what we're going to do is try to combine everything that we've just learnt and look at trying to find the image of the graph. So that's the new function with a dilation factor. And we can do it either through the dash method or just by looking at it. If you feel confident enough to just look at it, go ahead and do that. But I'm going to quickly do the dash method and then we'll confirm it through looking at it. So in fact, let's do that. If we were to have a dilation of factor 3 from the x-axis, we know that that means it affects the y values. So we would then assume that this function would look like y equals 3x cubed, because this is our y equals x cubed, and we're just multiplying by 3. But let's confirm it using the dash method. So if we were to very quickly do this, our new, if we were to apply it, x stays as is, y is 3 times. To equate, new x is old x, new y is 3y. Rearrange, so you don't have to do anything to x. Y is equal to y dash on 3. 4 is to substitute it into the function. And then 5 is to substitute or rearrange it again to get y by itself. Okay, now I forgot to write the cubed. When there's a dash, you can put brackets around it and then write the cubed, or you can leave it. But it's just, if you were to see, if I write a 3 there, it's kind of confusing. So generally we'll write brackets around it to show that. Okay, so either one works. You can see how that once you get good at it, you actually can go through the dash method quite quickly. If you can recognize it, go ahead and write it. If not, you can do the dashes just to make sure that you've definitely got the right answer. Right, so similar process now for part B, which is from the y-axis. So that is when we multiply our x values. Again, if you feel confident enough to just have a look at it and know what to put into it, go for it. From the y-axis, of course, is a little bit more tricky because remember, it's about the reciprocal. So if we were to just kind of look at it and be able to write it out, we would say, so we want a dilation of factor 3, so we've got y equals x cubed. Because it's the reciprocal and we are dividing, so that means we would divide all of our x values by 3, and then we would cube it. So this function is y equals x cubed on 27. Now I'm going to do the dash method just to confirm that that is correct. Again, remember the dash method is, if you follow it correctly, you can't go wrong. Whereas with these ones, you can easily make a mistake. All right, I'll just quickly write out all the steps. And let's go ahead. So step 1 is to apply. So all of our x values multiplied by 3, y stays as it is. Step 2 is to equate. Not sure what's going on with my pen today. It's enjoying going a bit nuts. All right, there we go. Third step is to rearrange. The y can stay as it is. Fourth step is to substitute into the equation. And then the fifth step is to get y by itself or to simplify or do whatever you need to do. Just notice that I do tend to leave brackets when I've got the dash there, because otherwise it kind of just looks like x to the 13. So the brackets make it very clear that there's a dash, and then we are going ahead and cubing it. So you can see that that there is correct. If you can remember to do the reciprocal, great. Otherwise, you've always got this method there for you as well. All right, last one now. We're going to be looking at example 5, which is about determining the factor of dilation when it's obtained by dilating a graph. So now we're kind of doing it the opposite way. We're trying to figure out what the transformation is rather than actually finding the new function. So it is a little bit trickier, and particularly because they've given us boundaries, because transformations can look different. Especially dilations. Sometimes you can write the same dilation from the x-axis or the y-axis. So we've been given specific instructions and we need to follow that. So this one says from the y-axis. So we're specifically saying to ourselves, x times what is going to give me this function starting from this function. Now, the technique for trying to find transformations, we're going to be doing a lot more of this later on in exercises as well, is to be able to, it's almost like going backwards. So you want to get everything that is related to y on one side and everything that is related or affecting x on the other side. So for example, if I have a function that's like this, y equals x squared plus 2, this plus 2 is related to the y. So I would take that over because that's a y transformation, not an x. If I have something like this can actually go both ways. So either that's a x transformation, as in from the x-axis, or if they wanted me to do it, sorry, that would be from the y-axis, or if they want me to do it from the x-axis, I can actually multiply it over, and now it's a y transformation. So it's really important for you to be able to distinguish the two. And depending on the question, so if it's something related to x, we leave it on the x side. If it's something related to y, we take it over to the other side. Okay, so in this case, because it's related to the x, we don't have to take anything over. We can leave it as it is. The first step that I will always do is to kind of write out my two equations. So this is what I'm starting. This is the old, and this is the new. And then I would rearrange the new into the format where all the things that I need for the y are on one side, all the things for the x are on the other side. So that would be the first step. First step is to rearrange the new function to have all the y stuff on one side, all the x stuff on the other side. Thankfully, we've actually already got that, so we don't have to change anything for this round here. Now, the second step is to actually equate the two equations. So remember, this equation here has turned into this equation here, and that's the rearranged format. So what I can see is that the old y is simply equal to the new y. So this is all the transformations that has been applied to the y. Nothing's happened here. So y will just be equal to the new y. When we think about x though, and we don't need the square root because we're just thinking about the actual x itself, the square root is the same for both, we can see that the old x is equal to the new x times 4. So you can kind of see that this is very similar to what we were doing before, we're just kind of working backwards. Now the idea is that we want to be able to tell the story of what has happened to our old x and to our, or what transformation is happening. So remember, when we're defining it, we've got x dash y dash is defined as blah, blah, blah. So we want to find out, okay, x dash equals what? Y dash equals what? So we're trying to figure out what has happened to old x and old y. What's their story? So the third step is to rearrange again. But this time, what we're doing is we're trying to get x dash and y dash by itself. Now the y just stays as it is, that's fine. In terms of x though, I can see that that's been divided by 4 in order to be able to get to x dash. So then the fourth step will be to describe it. So we're working backwards. It's all of the steps that we were doing before, but backwards. So in terms of y, there's really nothing that's happened, but we can see that all of our x values have been divided by 4. Now, how do we write that? We say there's a dilation of factor 1/4 from the y-axis. Okay, and that would be the transformation there. All right, so maybe a little bit confusing in terms of all the steps. You can kind of hopefully see that we're just working backwards from what we had before, but we'll be doing a lot more practice on this in future exercises as well. All right, let's try this process again, except this time we're going to do it from the x-axis. This time, that means that we're multiplying all of our y values, not by 3, by something. 3 was from our previous example. So we're multiplying all of our y values by something. So when we're writing out our two equations, so we've got our old and then we've got our new. Remember, we want to get everything over to the other side that is related to y. And because it's affecting y, that means this root 4 needs to go over to the other side. So step 1, which is to rearrange, is now going to involve a little bit more. So we're starting off with root 4 x dash. Now I want to get rid of that root 4 because that wasn't there in the original function. Not that I want to get rid of it, but I want to take it to the other side because it needs to affect my y values. So first of all, let's just get this separated. Now root 4 is of course 2. So that is the same as saying 2 times root x. Now, as we said, we want this 2 to be affecting the y. So I'm going to take that over to the other side there. All right, so now I can see what has happened to y dash or y in order to get to my new function. So second step is now to equate, and everything should kind of flow from here. So this is my original, this is my new. So the old y is equal to y dash on 2. And the old x, well, that's just equal to new x. There's nothing really that's happened there. Now, the third step was to rearrange to get x dash y dash by itself so that we can understand the story of the new. So that would be 2y, x just stays as it is. All right, and then the fourth step is to go ahead and describe. So nothing's happened to the x values, but I can see that all the y values have been multiplied by 2. So we've got the dilation of factor 2, and we write that as the x-axis. Okay, now this example is a little bit more complicated. And as I said, we will be doing a lot more practice on this later on. So that is how the process that we do it. Again, if you can just kind of look at it and figure it out, that's great. But for me, I would much prefer to actually go through this process, even if it takes slightly longer, just to make sure that we get the correct answers. Okay, hopefully you enjoyed this introduction to transformations, and we'll be back later on with more.